Now that we have built up a sufficient level of knowledge of R, as well as how to load data into R, we're going to start leveraging R from a statistics and probability perspective. Now, before we get into the probability component of this, because as I've mentioned, a good part of our course is probability, not so much statistics, but probability. And as we've mentioned, the reason for this is because a lot of the other areas and sub areas of data analysis are dependent on probability. So that's why we're putting such a heavy focus on this. But before doing any of this, to somewhat help us motivate some of the concepts in probability, we do like to turn our attention to data, because data is what, after all, has motivated some of the theories in probability, so to speak. So what we're going to do in this video is go through a few different things in R. Predominantly, we're going to talk about how to do just a basic exploratory data analysis. Usually this is what we do anytime we load a data set into R. We always start with an exploratory data analysis. So you'll learn how to do that after this video. It shouldn't take us too long. And the second thing that we'll start going through are some aspects of probability. And the remainder of this course, we will be leveraging probability, leveraging R into our probability discussions. So unlike what we went through in the first lecture, where it was just strictly the whiteboard, you're going to see me going back and forth between whiteboard and R, because R allows us the ability to illustrate some very nice concepts in probability. And now that you have some sufficient knowledge of R, I want you to be typing along with me, if possible, as we're going through some of our lecture material here. Okay, so let's get to it. So in the previous video, we had loaded in our data set into R, and if you don't remember what that data set looked like, this was some credit data regarding individuals, some information regarding about their background and whether or not they had defaulted on a loan that they had taken from the bank. And the idea is essentially that we wanted to, use this data to construct an equation to predict for new applications that come in whether or not that person is going to, or is fairly likely to, default on their loan. So anyway, we did the head command there on the data, and you can see us get some information on all of our individual pieces of information. Now, the way that we conduct our exploratory analysis is by two ways, three ways, really. The first is through a basic descriptive analysis. We then go through a visual analysis, and then we kind of combine the two for correlative analysis. And for descriptive, and same subcategories for here as well, we have two methods of doing this, and it depends on the type of data that we have, whether that data is categorical or numerical. All data is considered to be either numerical data or categorical data. So for example, checking balance here, this is categorical data because it's not numerical. Months of the loan duration is numerical. Credit history is categorical for purpose. Amount is numerical. One quick way that we can understand whether or not these are categorical or numerical is to use the str function on our data frame. And the str function, what that does is it lists out every single variable in the data frame and what type that variable is. If it is a factor or a piece of text, then we consider that to be categorical data. If it says integer, double, or any of the other numerical types, then obviously it's numerical. We do need to be careful though here, because sometimes the researchers who gather this data will do what's called code the data. And R tries its best to figure out which data is actually numerical and which one is non-numerical. And from what I can see here, it looks like it actually does a pretty good job at guessing, but this is not the case for everything. So for example, suppose that the fact that the variable default was listed in terms of 0, 1, where 0 was a code that represents that that the person did not default, and 1 assuming that the person did default. In that instance, R would assume that that is a numerical variable despite the fact that it's categorical. So the first step before doing any analysis is to ensure that R has correctly interpreted all of our variables here as being either an integer or a non-integer. Namely, what we're really looking for is an integer, double, or whether or not it's a factor. A factor is just a quick way for R to get the different categories, and each factor has different levels. Basically, each level is its own category. And you'll see those categories listed out. For example, whether or not somebody owns a phone, you'll see that there are 2 levels here, no and yes, okay? And then what R does is replace the no or yes with numerical values. The reason it does this is to minimize the amount of space that R is actually using, because numbers are much shorter and much less space occupying much less space than the actual text information. So those are the basics here of understanding. Now let's suppose we had the situation where we had, and I'm just going to, here's what I'm going to do. I'm going to take the data and do default, right? And I'm going to see which ones equal yes. Okay, and what I'm going to do is create, and I'm just doing this to illustrate a point here, but so you don't need to really follow along with me per se, but you could if you want to. So what I'm going to do is create repetition of the value 0 1,000 times. Create REP repeats the same value a certain number of times, so that's going to repeat the number 0 1,000 times, store it in a variable called default. Then I want to look at which values are equal to yes, and I want to replace the values in my default vector for yes at the same indices and set that equal to 1. So basically what I've done is convert the yes to 1, the no to 0. Okay, and now for data default, I'm going to just set that equal to my new default here. And there you go. So now you'll see that default is 0, 1. Let's just suppose for the moment that this is what it naturally was when we plugged it in. That is, a researcher had coded up 0, 1 for these specific categories. And rather than having yes, no. If you look at the structure of the data now, you'll notice that default is being read as a numerical value. This is problematic because we don't want to analyze that variable as a numerical variable. The 0 and 1 has no numerical meaning behind it. The 0 and 1 has only categorical meaning behind it. That is, either this person did not default or this person did default. But it has nothing to do with anything like count-wise. So basically, The problem here is we want to ensure that this number is not a number, but actually a factor. So there's two ways to do this. The first way is to either replace all of the zeros with some type of character, in this case, no, and replace all of the ones with another character, let's say 1. That's the long, frustrating way. There is a shorter way, though, to fix this type of problem. So again, suppose you imported this data set and the default here showed up as numerical, and you're saying, no, 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 this is not a numerical variable. This should be categorical. In which case, you can fix this problem very easily by keeping the 0, 1, but telling R that these are not numbers, they're categories. Just keep them labeled as 0, 1. And the way we do that is with the using the as factor function and plugging in the default column from the data frame. So when you do as factor, just run that function on its own and see what it does. Notice you get all the same values and these look numerical, but because you see the levels underneath, that means R is now actually considering this as a factor. That is, in short, it's considering it as a categorical variable rather than as a numerical variable. So if you do that and you take a look and see what the structure of the data then looks like, you'll notice now that despite the fact that the factor levels are 0, 1, that indeed they are a factor nonetheless. Now that you've converted, by the way, you can very quickly change the names of the factor if you want to by looking at the levels, of the defaults. So you'll notice that the levels are set equal to 0, 1. You can change this by specifying a vector of the same length corresponding to each one where the levels currently are. So the first one is 0. I can say replace all zeros with no and replace all ones with yes. And when you do this, now what you get, okay, is no and yes instead of 0, 1. So we've essentially gone back to what we started with when we first imported the data, but I went through this little exercise with you to illustrate an important point, which is that not every single variable here is going to be properly interpreted by R. You, the analyst, you're the one who needs to first inspect the structure that the data that R brought in. And then you need to tell R, hey, no, this is not categorical, this is numerical, or vice versa. Hey, this is not numerical, this is actually categorical. You will have some situations where R will read a column in as categorical when you actually intended it to be numerical. And usually this comes as a result of a typo in the data set. Somebody accidentally maybe put an L instead of a 1. Now R is going to say, well, I see a non-numerical character there. I'm therefore going to assume that these are all categories. Be careful with that. So step 1 of loading your data in, after you've loaded it in, inspect each variable to make sure that it actually is identified as the correct type of being numerical or as a factor with the appropriate levels. You can change the levels if you so wish. That's another thing you can do. But basically, this is like what we like to refer to as the pre-processing phase of analysis. We like to go through the data and clean it up, basically, to get it into a form ready for analysis. The next step is to go through what we like to call the descriptive analysis. And the descriptive analysis basically is just simply summarizing everything about the data set. It's aggregating things into, if it's a categorical variable, pardon me, it's just simply getting a sense of what the proportions are and the counts are in the different categories. If it's numerical, then it's getting a sense of what we like to call center, spread, skewness, and kurtosis. And there's other ones, but those are your four major ones we like to look at. And then once you've gone through your categorical and numerical analysis, you then move to a visual analysis, which we'll get to in just a moment. In terms of the categorical, here's what we do for categorical analysis. There's really not much to do. There's two things that we can do, which is to compute the proportion. I'm sorry, let me take a step back. Compute the counts of each category in the data set for that variable. Compute the proportion of each category in the data set, or compute the percentage, which is just the proportion times 100. So let's take a look at how we can do this in R. What we can do is, let's just say, let's take checking balance, for example. What we want to do is get a table of counts, which can be done by using the table command, on the checking balance variable. And you'll notice if we do this, that we get the following output. You'll notice, all right, that the reporting of the table is mainly due to the ordering of the levels here. So if we had wanted to, well, we have to be careful here, but I'm trying to remember now. I don't want to get into the ordering at the moment. It's a little bit outside the scope. But here's the point that I wanted to show you. Here's what R did. In the data set, it computed how many times somebody had less than DM dollar amount, less than $0 in their checking account. How many times did they have between $1 and $200 in their checking account? Pretty sure that's what this is referring to, if I'm not mistaken. And how many times they had, how many people had more than $200 in their checking account. And this is the number of times that are unknown based on the application, meaning somebody just didn't answer that question. So these, out of 1,000 people, these are the number of people in each one. We can very easily compute the proportion of these by repeating the same exact thing, but dividing it by the number of rows we have in the data. And that will compute for us a proportion, which are numbers that lie between 0 and 1. And the way that we, of course, interpret proportions is the same way we interpret percentages. We just simply multiply them by 100 to get a more of a percentage feel for this. So 27.4% of individuals had less than $0 in their account. 34.9% we didn't know, sorry, 39.4% we didn't know what they had in their account. 26.9% of individuals had between $1 and $20, and 6.3% of individuals had more than $200. So that's basically how we compute a very basic type of analysis. Now, we can shorten our analysis here by just simply extracting the categorical data by providing it just simply either the names of each column, which are too much for me to do at the moment, or the column number here. So here here's column number 1. Then we don't want 2 because that's an integer. We want 3 and 4, 5, 6, and 7, 8, 9, 10, 11, 12, 13, 14, did I miss something? Hold on. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 17. And that will get us the data just specifically for the categorical datas. So you'll see that in this data set, I've eliminated all of the categorical data. Numerical data, I can do the same thing and split it up by just looking at the numbers that aren't in there up to 17. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So basically all I did was just split the data between numerical and non-numerical. And to be honest, there's actually a faster way to do that, but I want you to get used to working with the data frame itself. So as you can see, I now have all purely numerical data. And actually, I should have probably done that up there, but that's okay. So split data into numerical and categorical. Okay, now we can shorten our categorical analysis. Instead of going one by one through each variable, we can actually use the summary command on the entire categorical data. And what R will do is actually compute all of the counts across every single variable. You can further divide that by the number of rows you have in the data set. Just be consistent there. No, you can't do this. Sorry, I forgot. You need to go one by one, because here in the summary, okay, if you take a look and see what gives you back, and you look at the structure of this, you'll see that it gives you a table. I don't recall what type table is. I think it works off this system. Oh, I didn't want structure, sorry. No, okay, yeah, it's giving us strings, that's why. Okay, so ignore summary. Let me see if table does it. I forget if table easily. Does this. Oh, no, we don't want to do the table. Table is going to do something very complicated that we don't want to do. Keep it to summary. Ignore everything I just said. Sorry. So basically a very quick way to just get at least the counts is to just use summary. Here, though, I'm fairly sure that because these are now strings that it's returning back to you, you can't get the percentages. So what you would need to do is go variable by variable if you wanted to compute the percentage tables. You can actually define a function to do this, and perhaps I'll leave that as an exercise for you to do. But anyway, that's how we can do a basic descriptive analysis on the categorical. Notice that we get counts, and we get a sense of what each we get a sense of what the frequency of each category looks like here. Okay, so next we have the numerical variables that we want to analyze. And when it comes to analyzing things numerically, what we like to look at is predominantly what we call center and spread. Measures of center include the mean, the median, the mode. Measures of spread include the range, the variance, the standard deviation. And then we have two other measures, which is what's often referred to as skewness and kurtosis. But I'm not going to get into those today. We'll just focus on center and spread, since these are the two most frequent type of measures that are used. The other last thing we like to do with numerical analysis, descriptive analysis, is come up with what's called a relative frequency distribution. And that's basically to get an understanding of what or how the data is spread out based on categorizing the numerical data into different buckets. So anyway, let's get a feeling for the numerical data. So the first thing that we do is look at the center. And we've already mildly touched upon this. So let's take, for example, what do we have in num data? The month's loan duration, how long the month's loan was in terms of the number of months. So let's do some basic numerical analysis. We can do this by finding the mean, the mode. I remember, is mode in here? Yes, mode is in here. The reason I ask is mode is really not used as often. Okay, it appeared to not give us back anything. That's fine. The median is used. Median and mean are used the most often. Mode, not so much. So those are our measures of what we like to call measures of central tendency. They describe roughly where the center of our numerical data is. So notice that the mean and median are different. Okay, if you haven't gotten to this point in your education yet where you've had an intuitive sense of what the differences of these are, the mean represents a balancing point in the data. That is, it's the point on an ordered scale where all the data to the left of that number in sum will balance out all of the data on the right of that number in sum. In sum, meaning mainly in terms of distances from this point. The easiest way that you can think of the mean is imagine that you have a ruler with a bunch of 1 pound weights, and the ruler, your data set only ranges, let's say, from 1 to 12. So you can only get numbers in your data set from 1 to 12. And for every data point that you have, suppose you put a 1 pound weight on that number on the ruler. The interpretation of the mean would then be, where on the ruler should I put on a pin coming from the ground such that the left balances out the right? All right, so that's sort of the physical interpretation of the mean. The median, on the other hand, represents the 50% mark in an ordered data set. It represents, if I were to order the data from least to greatest, what number is it such that 1/2 of my data, 50%, if I had 1,000 people, what's the point, the number of months, let's say, such that 500 people have a loan, in this case, less than or equal to 500. I'm sorry, not less than or equal to, less than or equal to that number. Mean and median greatly differ in interpretation, and we have to be very careful with using either one. When we're talking about statistics, a lot of people like to use the mean, but we're finally starting to see a revolution here in this, because I don't know why, but I'm assuming that a lot of people have just finally started to come on to the idea that the mean is not exactly quite representative of a data set. And you'll understand why as we start to progress forward. Median is a little more representative, but it depends on the applications. It's really hard to say that, yes, I'm going to look at average and say that summarizes my data set pretty well. No, that's not really a good thing to do. Whenever you're looking at data, you need to take the data as a whole entire data set, not just looking at one number, which is the mean, which unfortunately we've been doing in math and science and the natural and social sciences for quite some time. However, we have to be careful with interpreting what that number actually, with no pun intended, means. If I were to talk about, for example, the average price of a home, I don't care about the average price of a home. If I'm looking for a home, I'm going to look for the median price of a home, because it's very plausible that I can have a data set, let's say, of 10 homes in the neighborhood, one of which is up for sale, say I have this. Let's say I have homes that are worth $10,000 each, and I have one home that's worth $3 million in that neighborhood. Suppose I have a really, really dedicated citizen that came back and opened up, built a house in that neighborhood, and it's sort of a house that kind of sticks out. So here we have all of the homes in the neighborhood worth $10,000. And here we have one home that's worth $3 million. But obviously I'm not going to go for the $3 million home. If I'm looking for neighborhoods and I'm judging what's the worth of that neighborhood, I don't want to be really looking at, or what's the typical price of a home in that neighborhood more appropriately. I don't want to be looking at averages, because if I do, here I'm given the impression that, oh, most of the homes, they're around $309,000. But yet again, here you go. Here's a neighborhood where all of the homes are actually in the $10,000 range. And we only have a handful of the other homes, which are very high worth, which are dragging that mean all the way up. So here's the point. The mean is not exactly a representative measure of the population. We tend to, in these situations, when we want something a bit more representative, is to look at the median, which obviously will give us the more appropriate value of that. So what is the mean? The mean is a balancing point. The median, on the other hand, tells us at what point is it such that half the data set is less than or equal to that number. Here, the mean is $309,000, which tells us that all 9 homes on the left of 309,000, if we were to take for each data point $10,000, okay, and I'm just going to repeat it this time. I have it. Nope. Where is it? If I were to take all of these here, okay, and see what's the distance from 309,000, you'll see that I get these numbers here. And if I were to add up all of those distances, I get that number there. If I were to look at the distance from my $3 million home and away from the mean value, which is, as we said, 309,000, you'll see by magic, you'll get the same number. And that's not by magic, that's by design. Put differently, the sum of the distances of all the data points from the right of the mean should always equal the sum of the distances of the data points from the left of the mean. That's by design. That's why the mean is the mean. The mean is a balancing point. It's where all of the data on the left, in some sense, balances out all of the data on the right in value. The median doesn't really care about the value. All the median cares about is first ordering the data and then counting counting the number of individuals. So if you want to think about it, and going back to our block example on the ruler, you find the median by simply going from left to right and counting half the number of data points that you find. And once you get to half, wherever you land on the ruler, that's your median. Why? Because approximately 50% of the data, 1/2 of the data set, have values less than or equal to that number. So in the case of the home, here we see the median was 10,000. That says that half of my data, 50% of my data, is less than or equal to $10,000. The other 1/2 is bigger than or equal to $10,000. All right, so that's the median. The mode is the most frequent, but I'm not going to have a discussion on that because it's a pointless measure, to be honest with you. Not pointless in statistical theory, but more for practical purposes. It's pointless. by the way, we can come up with other metrics. The other things that we like to look at is what we like to call measures of dispersion, which tell us how dispersed the data actually is. So we have three major type of metrics we like to look at, which is the range. So the range tells us the distance between the small and low number, the minimum and the maximum of the data. Unfortunately, R just gives us the minimum and maximum. You can write some code to find the difference of this if you would like to. The second measure of dispersion we like to look at is variance. I'll have a separate discussion on this at a later point in time, because not everybody understands the intuitive idea of variance, which I understand, but in essence, variance represents how much on average the data points are in a square distance, at least, from some center point. Usually we pick the mean to be that center point. And then we have the standard deviation, which is the square root of the variance, which is not exactly the same, but it's a rough approximation to the average distance of any of the data points from the mean. So range is not a great way to measure distance, because the spread of the data can be very compressed in one area, but I have two outliers. And in a different data set, I may genuinely have those same two minimum and maximum numbers, but the data is much more spread out in terms of what values we're observing in the data set. So that's why we tend to look at variance and standard deviation, which gives us a much better picture of how the data is spread out relative to a point. The range is a metric that's not really relative to a point. So here you can see if I take the difference between 72 and 4, I get 68, which gives us the idea that my data is spreading out by a total of roughly 68 units. If I take that by, let's say, 1/2, that's what, 34. So here I have the scenario where I think the spread is approximately 34 from the middle point, but yet when I look at the standard deviation, which is a much better approximation to the average distance in the middle point, what I ended up getting is not 30 something, but actually 12. So the spread is much less than what we initially imagined. So anyway, measures of central tendency give us a picture of where the center of the general data lies. Measures of dispersion give us a sense of how spread out that data is. And then the last thing we kind of look at is this notion of quantiles. Quantiles, and we usually look at 3 of them. The median is an example of a quantile. Quantiles tell us similar information that the median does, but except instead of looking at 50%, we look at 25 and 75. So what is the value such that 25% of the data has a value less than or equal to that value? What is the value such that 50% of the data, in order data, has a value of less than or equal to that point? That's the median, or what we like to call the second quartile. And then the third quartile, which is a version of which is the 75th quantile, we like to look is the point that is the number that such that 75% of my data set has a number less than or equal to that number. So when we have this here and we do, let's say, 25%, oh, not quantiles, quantile. Okay, here you'll see that we have the number 12, which says that 25% or 1/4 of the applications had a month loan duration of less than 12 months. We do this also with the 50%, which is the median. Now, I'll forewarn you, this may not be the same, simply because, and it happens to be the same, but simply because the median can actually be found in a lot of different ways. When you learn the median in the basic stats course, you're not learning the equation of the median, you're learning actually an approximation to the median. So the real median is a lot more complex, and there's a lot of different approximation methods to it. So sometimes you'll see some inconsistencies across software packages and even within R itself. But regardless, we still, they still provide somewhat adequate approximations. And in this case, we didn't have a problem because, as we can see, 18 happens to be the same. The median, by definition, is the 50th quantile. And then we have 75, which is what we often refer to as our third quartile. So what you like to look at is first quartile, second quartile, which is the median, and third quartile. This gives you a picture of how spread out the data lies. So 1/4 of our data has applications that are less than 12 months or equal to 12 months. 1/2 of our, I'm sorry, 1/4 of our data. 1/2 of our data has applications that are less than 18 or equal to 18 months. And 75% of our data has applications that are less than or equal to 24 months or 2 years, which means that the interpretation here is approximately 25% of our data has something more than 24 months. If you look at the minimum and the maximum of the data, which you can also do using these, minimum and maximum, that's just the range. Notice that 25% of applications are longer than 24 months, but the highest application, 72 months. That's a big spread in the data for just, let's say we had 100 people, for 25 people. That means those 25 people have a lot of spread in the different lengths of applications. But if you'll notice that that spreads much less for the same number of people between the 50th and 75th percentile. That means that another 25 people, despite the top 25 people having very, very different lengths, the same number of people had much, much shorter lengths. And this gives us a sense or an idea in our head about how concentrated the data lies in terms of months in this case by looking at the ranges. So we tend to look at the quantiles to get a sense of what the distribution of the data set looks like. We can do all of this with the summary commands without having to go by hand here. The only exception is summary does not give us the variance and the standard deviation. Luckily, you'll notice we get all the same metrics we just looked at, by the way, with the exception of measures of dispersion. Luckily, we can use the apply function. This time we use what's called the lapply function. I'm sorry, just the apply function, which is similar to the sapply function we reviewed through in a previous video. Unlike sapply, the regular old apply function is applied to a data frame. And in this case, we have 3 instances. The 3 inputs. The first input is the data set itself, which in our case is just numerical data. The second input is how we want to apply the function. Do we want to apply the function to every row and get back out a vector where the function was applied across all the rows? Or do we want to apply the function across the column? In this case, if I want to find the variance of, let's say, every single column in the data, I'm going to do this by columns. The way we specify this is with the number 1 or the number 2. Number 1 specifies do this by row. Number 2 says do this by column. And last is the function to which I want to apply to every single column, which in this case is just variance. So let me illustrate this very clearly to you, okay? You'll notice that if I wanted to find the variance of each single one, I would need to do this. Let me do num data. I would need to do this one by one, which becomes, well, painful. And I can certainly shorten up my time typing by doing some copying and pasting. Okay. Percent of income, years at residence, age, existing loans, dependents. Okay, so yeah, sure, I can do all of this one by one, but as I've just illustrated to you, that's kind of a pain. So I want some way to tell R, hey, apply the same function, VAR, to every single column in my data frame. And the way we can do that is with the apply function. We're telling R, hey, apply the variance function to every column in the data frame num data. And when we do that, you'll notice that we get the same exact numbers that we got here, except obviously we didn't have to repeat the same command over and over again. So if I wanted to find the measures of dispersion very quickly, I can do that using the apply function with the different measures of dispersion and any other measures, of course, that I want to come up with. This is minimum and maximum, okay? So on and so forth. So that's a basic descriptive analysis for data sets. We look and try and understand the spread. Where does the center of the data lie? How spread out is it? What do the different quartiles look like? Usually what we like to do as well is come up with a relative frequency distribution of the data. So I'm only going to do this for one of them. Let's say age. And the way that we do the numerical distribution is by using the cut function. And basically what we're trying to do is, because we have numerical data, we're trying to group the numerical data into different buckets and then come up with counts of how many times we observed the different buckets. So this way we aggregate the data on a more of a granular level. We can't count the number of numbers because there's too many individuals who have different numbers. So instead, what we like to do is group the numerical data together to be able to get a better understanding of how exactly it's distributed. And one way of doing that is using a function called the cut function, where what it's going to do is we specify how many breaks we want to break. Think of it this way. It's going to, R is going to look at the age data and look at the minimum and the maximum of the age data, which we know is between 19 and 75 years old. And what R is going to try to do is break that large interval up into either intervals we give it or a number of intervals that we give it. So let's say I break this up into 3 basic intervals: young, old, young, middle-aged, old. Okay. What is R going to do? It broke it up evenly between 18.9 and 37, 37 and 56, 56 and 75, and then it converted each number to an interval. Just so you can get an idea of what's going on here, let's store that in a variable, and let's kind of look at together in a data frame the age and the cut ages, just so we can illustrate what's happened here. Basically what R did was it tried to figure out what are the 3 intervals I'm going to use, and it's taking each age and finding which of those 3 intervals it's going to replace that number with. So in this case, it replaced 28 with this interval. It replaced 32 with this interval. Notice these are 2 different numbers. So if we were to just do a straight count of how many times we saw that number, these would go into different buckets. But because we're only focused on 3 buckets, what R did was assign each of these numbers into the same bucket. So now we can get finer or more broader rather counts to start to understand the structure of this data. Once you have the cut ages, you can do a table of the cut ages to get a sense of how many individuals lie in each range. You can further refine this process by increasing the number of breaks here, and then again, going through the table of counts. Technically, what you really want to do is look at this here, which converts the counts to percentages, and what we end up getting, what happens? I'm sorry, not cut ages. Data. What we end up getting is a relative frequency, what's called a relative frequency distribution, which gives us the percentage of data that lied in each of these intervals. And this gives us a sense of where most of our data lies. So as we can see, most of our data in this data set comprised of people who were less than the age of 41, but older than the age of 18. We can further refine this by using more intervals. So instead of using 5 intervals, we can use, let's say, 10, 15, 20. We start to lose information as we decrease the number of intervals or increase the number of intervals. A general rule of thumb is to use anywhere from 10 to 15, or I'm sorry, 5 to 15 intervals. But this is an entirely subjective process. There really is no reasoning as to why we would use this number of intervals or not. It's just a standard common rule of thumb that we use in stats. So as you can see, we see it's pretty uniform with the exception of ages 24 to 30. We see that that tends to be the highest age group right now. We can break it down even further if we wanted to into, let's say, 15 different age groups, where we see that the majority, or not majority, but plurality of this appears to be between people between the ages of 22 and 26 and 26 and 30. So we're, as you can see, we're getting a sense of what the distribution looks like. We have some people who are 18, but not many, a lot of people who are in their 20s, and then we have some people who are in their 30s, but there's really not that many people in our data set who's applying for these different applications. So this is the process of descriptive exploratory analysis. We're just kind of looking at what is our data telling us in terms of how it's structured. Now, up to this point, we've done everything numerically, but as it turns out, we can do these visually. So one thing that we can do is we can come up with different plots. Like, for example, I could look at a bar plot of my cut ages that I have here of my relative frequency distribution. And as you'll see, we're able to get a nice plot that tells us the different intervals here, where the y-axis is the relative frequency and the x-axis, that is the percentage of cases in that interval, and the x-axis is the interval itself. We can do this with, we always need to make sure that we have a table here. You can't just use raw data. You need to make sure you have a table where a named table, where you have a name and then either a count or a percentage of the two, in order for R to properly interpret what's going on here on the plot. You could do the pi, which, let me see if this will work. I always mess up the pi. Nope, that worked. So we can do a simple pie chart and see what's going on here with the different intervals if we so wished. But technically, because this is numerical data, we actually just simply look at a histogram of the age data and let R do the work for us. So the histogram R will just break it up automatically for us. There's different properties of the histogram we can change. Okay, we can color it and whatnot. We can change the main text here. And technically it's a distribution of ages. All right, so there's different things about the plot that we can change if we wanted to. We can change the X label, for example, to be the age, the Y label to be the frequency. Okay, you'll see a change to those figures there. But we're not just restricted to histograms here in terms of the number of categories that it gives us. You can actually specify this. Let me take a step back. When we have lots of inputs into functions, as a side note, I like to just drop these down with the enter button, and R will still be able to read it, but it keeps our inputs in a much more organized fashion. But anyway, that's just a preference. You can leave it as any way you wish. Here, you can actually use the breaks function, similar to what we did with the cut. And you can choose the number of lines that you want to have show up in your histogram. So it looks like we already had 10. Suppose I want to refine the histogram even further. So it doesn't look like it's doing this. Let me try again for 20. There we go. So as you can see, as you increase the number of breaks, R is going to give you more intervals here. But be wary, because as we mentioned, as you increase the number of breaks, let's say you break them up to 50, you're going to start to lose information here. You're not going to be able to decipher. So this is some pretty good information, but let's say we did 1,000 breaks. You're going to find very quickly that we don't have, that much information, that a lot of it's going to start to get lost if we get too granular. So what we like to do is just pick a simple number here. 10 to 15 is usually it, but sometimes this, on occasion, you feel the need to go more, just to get a real sense of what the distribution itself looks like. A lot of the times you'll see a lot. These are ages, so you're going to see overlap. But a lot of the times you'll see numbers that won't overlap. Like, let's say, for example, percentage of income. Let's take a look here. There's a lot of overlap there. Okay. Let's choose a different one. Amount. Okay. So let's do breaks equals 100. See what happens. Okay. What about 1,000? 10,000. You see what's happening? We're losing information here. As we start to refine more and more into the number of intervals, we're not getting that much information. As we start to decrease our number of intervals used, we're getting more information. But as we start to decrease too much, we again are losing information. So there's a perfect amount in between that we want to look at with our histograms. So for categorical data, we look at bar plots, pie charts. And by the way, you can do the same thing for the, let's say we want to take a look at how many people identified what type of job they have, okay? If you take a look and see at the table, remember the table command is giving us counts for each category, right? Each category. When we run the pie command on that, we're getting these different percentages here. in the pie. You can alternatively do a bar plot on the table of the categorical data. And get something similar. Okay, so those are some basic plots. Last, in terms of plotting, we have what's called, similar to a histogram, but slightly different, which is what's called a box plot. And this also is specifically for numerical data. We tend to look at a lot of these as well. Oops, misspelled that. Box plot is read as follows. On the bottom here, the very thin line, you'll see the minimum. Then it has dotted lines. It has the first quartile. The thick middle line is the median. The line here is the third quartile, and the top line here is the maximum, and then R identifies the rest as just simply outliers. You can turn the outliers off and focus strictly on the minimum to maximum. Okay, and get rid of them. A note on outliers. I don't like the word outlier. Outliers are a very subjective type of process into determining whether or not you should consider a data point as an outlier or not. There's a lot of methods of doing this. And there's a lot of actual philosophical debate on whether or not we should even worry about outliers or not. Statisticians do agree that the concept of an outlier, a data point way outside the range, will cause some problems in statistical methodology. That's not where we disagree. We tend to disagree with each other in terms of whether or not we should throw the outlier away or keep it in our data set. I tend to be on the camp of leaving it in the data set because that's an important piece of information that we could be throwing away entirely, which may lead us to some interesting conclusions. And so typically what we like to do is transform the data sets to reduce the impact the outliers have on our analysis. There is a second camp, which I entirely personally disagree with, professionally disagree with this camp, which are those who like to throw away the outliers. To me, that's throwing away perfectly good information about your population. Regardless, whichever side on the debate you lie on this, outliers in terms of just simply removing them, if that's what you so wish to do, is in your plot here is just simply done by using the outline equals false option. Anyway, here we have a box plot. You'll notice that it is very similar to the histogram of the same of the same here. Notice that on the lower numbers, we have a lot of concentration. In other words, the same amount of data points are here as there are here and as there are here and here. This is 25% of the data, 25% of the data, 25% of the data, and 25% of the data. But notice that the spreads are different and where those values are concentrated differs. So you'll see here a lot of concentration on lower numbers, a lot of concentration here. Not so much concentration. We start to see the values spread out, and then we start to see a lot of spread here in the upper. If you compare that to the histogram, that's the same idea. Okay, you'll see, wrong amount, age. You'll see the same idea here. A lot of concentration here, some concentration here. We start to see it, less concentrated, and then not so much concentrated here. Okay, so that's the general idea behind the concentrations there. So we have our plots, and let me just take a sidebar, so to speak, and preface this with, or no longer preface this, but remark that these are the core plotting tools from R. These are not the only plotting tools which can be used in R. Namely, there's two very important packages, which I'll start to slowly introduce you to, not today, but throughout the semester, that we like to use in our analysis. The first is the package ggplot2. This requires a lot of skill to use, but you can get some very nice, interesting plots. The second, which I tend to prefer more, is the package plotly. Plotly is another package we can bring into R, and it allows for interactive graphs to be produced from your data set, and very easily. There is another package called RShiny, which will allow you to create a web application very easily to allow others to access your data analysis and basically play around with a lot of your plots and see what's going on. I'm not going to get down into that level of granularity, but what I will focus on is slowly introducing you to plotly. I might throw something from ggplot2 in, but I don't want to go that far. Today, you should just know and learn to understand the basic plotting functionality of R. From there, we'll get to more intricate and pretty looking, more nicer looking plots that you can play around with to really get your data to shine, so to speak. Anyway, we have another set of plots and analysis we like to look at, which is correlative. And we will most certainly get into this discussion because we have the idea of correlation being a colloquialism for a relationship between two things. And when anybody talks about, well, there's a correlation between these two things, they're talking about some type of relationship. But when we talk about a statistical correlation, that has a very specific meaning, and we're usually talking about a specifically linear relationship between two quantities. And I'm even cautious to use the word relationship. I'll say rather association, and we'll leave it at that. But nonetheless, we like to see how two quantities may or may not be associated with each other. And typically the way we do that is by looking at a few different things. We can look at quantities where numerical quantities that we have on the independent and dependent axis. And we're looking at what we like to call scatter plots. So one way of looking at this, first let's get the names of our numerical data back, okay? The way we do this is through the plot function. So I might be curious, what impact does age have on, let's say, the amount? And we can plot those two and we'll get a scatter plot. I'm sorry. I forget if I can do data in this. No, I can't. So we have to explicitly write it out. Num data $, num data $. Okay, and here we have the scatter plot. So some might say there does not appear to be a relationship between these two. I actually see one, and it tends to be, it looks like it's curvilinear. But again, I've been trained in this, so I'm kind of used to it. As you'll see, there's a lot of concentration at points here, and you'll see that concentration somewhat looks like an inverse relationship. So there might be some, association kind of going on there. Others of the more naive eye might say that this is just random scatter and there's not really much there. But this is why we have statistical analysis, right? To help us remove some of the uncertainties away from our eyes and help us remove some of the uncertainty away from our eyes and uncover patterns that our eyes, might be deceiving. But we do like to look at scatter plots to get an initial feeling for, what could possibly be related and how. So what else might age impact? We might be curious to see if age has an impact on how long the loan is going to last for. We see some mild linear relationship here, not very much. There does happen to be a lot more scatter there. Let's see, what else might age have an impact on? Let's see, maybe perhaps percent of income. Okay, maybe not. Let's see, what else? Maybe the number of dependents. Okay, so we can see that younger ages tend to have a little bit more, tend to have 2 dependents, while the 1 dependent is much more spread out by age. Let's see what else. Maybe maybe the years at the residence. That's, I'm sure, going to be related to each other. And lo and behold, it is. There, we still have some spread, but you'll notice that we have a clear linear pattern coming this way. Okay, so this is the moral of the story. We're looking at, you know, how things are related to each other correlatively. We could do this by visual inspection, or we can do this by running the correlation function, which will give us a value between 0 and 1. So looking at these correlations, we see the strongest correlation is this last one that we had looked at. The other ones have fairly weak correlations. But remember, correlations only give us information on linear association, not general association. So it's entirely plausible I can transform one of these data sets into something else, and that something else will be correlated with one of my other pieces of data. We can also look at some visuals between categoricals and numericals. So for example, suppose I want to look at I want to determine what do the ages look like for, let's say, let me do categorical data. What do the different ages look like? What do the age distributions look like for those people who in different types of job positions? So I might do this, where I put the categorical variable first, and then I put the numerical variable. And what it's going to do is give me different box plots only for the data points of ages of people who fell under management. So I can kind of get a sense of how the distributions may be similar or different to each other across the different categories. I can do this as well with, let's say, a different categorical or numerical variable here. So instead of age distributions, I want to see, based on their job, is that going to determine the amount of the loan? Okay, and we can very clearly see that those in the management position tend to ask for higher loan amounts than those who are skilled, unskilled, or unemployed. So we're noticing some patterns there. We can look at categorical to categorical, by the way, and this will produce what is called a spline plot. So I could look at the distribution of people who have these different types of jobs determine, let's say, whether or not they have or how long they've been employed. Okay, and what we're looking for is differences in the distributions of these across the board. We do see there's some mild relationship. Those who are unemployed tend to obviously have, well, lower unemployment. On the other hand, those who are skilled tend to have longer years of employment. Same with those in management. And those who are unskilled also tends to be in line with skilled and management. So there generally does not appear to be any, real associations going on there. Let's see if we can find some any interesting ones here. Instead of employment, let's look at maybe credit history. That might be something we're curious of looking at. So we see that those individuals who are skilled, unskilled, or managed tend to have higher proportions of perfect credit score, good credit score, while those who are unemployed tend to have critical unemployment. So we noticed some interesting patterns that are there as well. Let's look at other stuff. So let's say for purpose is the type of job that somebody has. So as we can see, management's purpose and unemployed's purposes are fairly different from each other. We can see that those who are unemployed, and interestingly enough, those who are in management tend to use these for vehicles, while those who are with skilled and unskilled labor tend to use it more for appliances. But here, hopefully you're getting the point. We're doing exploratory analysis. We're playing with all the different permutations, so to speak, to try and get an understanding of what is our data set telling us. Now, I want to be very strict here. We can't conclude anything definitively off of a visual analysis. That's a really bad way of doing data analytics. We use visualization as a tool to reflect our analysis and then to help guide us like a compass towards our analysis. But we don't use it by any definitive means to justify our analysis. That's an improper way of doing analytics. However, visualization, as the name suggests, does help us gain a better understanding and kind of gives us hints on where to go in our official analysis, which we'll get to obviously much later in the semester. One final thing to note is that you can actually get a nice plot across all of your numerical data values by just simply doing plot and putting the data frame in there, assuming the data frame is full of the numerical values. And what R will do is automatically compute for you the different permutations of all of the scatter plots. Some of these are harder to read and you want to dig into, but it will give you a quick way of determining whether or not there may or may not be relationships. So for example, look here, the number of the amount on the independent axis and how long that loan is going to be. I'm sorry, this is the opposite. This is months duration. And the y-axis is the amount. You'll notice that there looks to be some linear pattern here. There also looks to be a pattern on the opposite way, obviously, because if there's a pattern here, we should expect there to be a pattern here. Just flipping it. We notice some linearity here and here. We notice some patterns here as well between the number of existing loans and the amount. We notice a pattern here between the existing loans and the duration. We notice some slight patterns here. So hopefully you get the point, right? The point is we're looking for these different patterns. I don't remember if you can do this, by the way, on the categorical data. I don't think so. I'm forgetting if it will do this for you. No, not really, because it's going to assume that you have numericals. So that you're going to have to do one by one, but maybe I'll leave it as an exercise for you to kind of, render automatically all these plots or something with a function or something to that effect. But anyway, this concludes our first lecture on R. Moving forward, we're going to just simply be integrating the aspects of R into our analysis rather than just hold a separate lecture altogether. But this lecture was very important because it has laid the foundation for you to start working with hands-on R. Moving forward, we will be integrating the different aspects of R into our analysis.